everyone. Thank you for being here today for my presentation, Rapid Flood Inundation Mapping. My name is Asad Murad, and I'm really honored to be here and showing you what we've done. Very quickly about me, my name is Asad Murad. I work for Stantec, and I live in Durham, North Carolina, where I completed my PhD at Duke University in 2020. Publishing on hydrology, the water, and carbon cycle. But in 2021, I joined Stantec as a data scientist, and we were just starting to make strides in data and AI, and I was able to ride that wave, and today I'm ML manager at Stantec. But Databricks has been a big part of this journey, and I'm very happy to be here talking about this. A lot about Stantec. It's a Canadian engineering and design company founded in 1954, based in Edmonton, Canada. Stantec employs over 31,000 employees across the 6 continents and ranked among the world's 100 most sustainable corporations. We offer a range of services in civil engineering, water, buildings, infrastructure, sectors, and others too. My team is really a small software and data team within the larger company, but we're making a mark. And part of the story is that we're majority environmental scientists turned data scientists and software developers. I hope to show you some of the progress we've made over the past years and some of the positive impact we've made on our communities. So this is what we'll talk about today. We'll talk about floods, an overview of floods, a brief history of the science, how flood risk is assessed today, and really what opportunities present themselves, dismantling some of the community barriers due to some of the ways today companies and communities get their flood risk, our geospatial data lakehouse, our data transformations, convolutional neural nets adapted to flood mapping. We're going to discuss that. And finally, how everything together comes in to produce very good results for our communities. So floods aren't all the same. Riverine floods, as the one I'm showing you here. So by the way, this is the most destructive river flood in the United States. It's the Great Mississippi Flood of 1927. It caused anywhere between $4 to $17 billion in damage, and hundreds of people died. River floods occur when the rivers overflow their banks due to, let's say, excess rainfall or snow melt. And typically, they develop over a period of days, weeks, or even months. You can actually see here, I don't know if you can see my laser, but on the image on the left, the levee was breached, not unlike what happened in New Orleans. Flash floods, however, develop way more quickly after the causative event. We're talking here within 6 hours of excess rainfall or a dam break, for example. And here I'm showing you photos from the New York Times from Vermont and New York floods of 2023. People usually underestimate the quickness, the rapidity with which the floods develop in case of flash floods. That's why you'll really see people stranded in their vehicles during flash floods because they don't realize how quickly they need to go to higher ground. And because of flash floods, you need to have adequate lead time, to know when the floods are occurring. And this is where we're making a mark. Last but not least are coastal floods. These occur in low-lying coastal areas, especially during high tides, when there are storm surges due to hurricanes, for example. But these are also exacerbated due to sea level rise because of climatic change. I'm showing you here an image of Hurricane Ian in 2022, a satellite image of it on the left, and damage to areas in Florida on the right. We are not going to focus on coastal flooding today. We'll mostly focus on flash flooding. Brief history. Flood science isn't new. Ancient civilizations, Asia and the Middle East, had early philosophical descriptions of the hydrological cycles and hydraulics. They had complex water engineering projects like aqueducts that you see everywhere and bridges. But it's not until the 15th century we've started doing at least recorded physical experiments in hydrology and hydraulics when Da Vinci undertook the first physical experiments, and you can see him depicted on the right measuring river flow with the tool he used. I have it on the bottom. In the 16th century, people have written observations of springs originating from rain. 17th century, rain and runoff start getting quantified in France. And in the 18th century, we closed the water cycle with measuring evaporation. In the 19th century, we finally get mathematical descriptions of fluid flow with Darcy, Dalton, Reynolds, and many others. And 20th century, we not only get fluid flow descriptions, but models of soil infiltration, evaporation, and other properties of the water cycle. Finally, in the modern era, everything culminates with the availability of high-quality data sets from remote sensing sources like satellites and GIS tools that allow us to calculate hydrology and hydraulics at scale. Okay. But really what defines the how here is how flood risk is assessed today. So I want to introduce you first to the concept of flood risk assessment. Flood risk assessment is the combination or product of flood hazard, which identifies the location of floods, the probability of its occurring, erosion zones. The product of that was with the damage and the consequences of these catastrophic events. And these happen by overlaying the hazards on top of the built environment. So critical facilities, buildings, vehicles, where different communities live. And this allows you then to perform mitigating actions to protect the population and better inform policy. But today, we'll be focusing on hazards. It's usually the first piece of a full-fledged engineering flood risk assessment for a community. So we'll really focus on how to speed up, how to make it more cost-effective to get the hazard data for all kinds of governments or communities or and so forth. The way engineering companies like Stantec calculate flood hazards today is by using physics-based models that are very complex and expensive to run. They need high-performance compute. So what these do is that they calculate the surface profile over your floodplain and open channels. And so given a storm or given a river flow, you'll be able then to tell where the water sits on top of a, let's say, area of interest. They work by solving a complex set of differential equations everywhere on a set or on a mesh of pixels on your map. So it's a high number of concurrent calculations. And so not only does it take a long time for engineers to set them up, but often due to regulation, it also takes them a long time to calibrate their models against pre-existing flood data like high water marks. What this means is that, in fact, a lot of communities, even in wealthy countries like the United States, do not have adequate flood hazard or flood inundation maps. So they don't have a good idea of which parts of their communities are most affected by floods or flood risk. And there's, like a lot of things, a lot of inequality of where that exists and where it doesn't. And this is just this slide just shows you some of the timescales that are involved in getting traditional flood results. A traditional study performed across the majority or the full United States, given current standards, would take a decade. The ML approach I'm going to present takes a year. And within a smaller watershed, like those used in the United States that are almost 700 square miles, it takes a day versus 270 days. So really here, what we're starting to do is dismantle some of the barriers communities have in getting the flood data they need, both in terms of time, getting timely data when they need it, and in terms of making it more cost effective. To do that, we borrow from an approach that's been used for a while now in climate science. I've taken this diagram from the KIT University. It's a renowned university in Germany. They have it on their website. And really what it shows is an Earth system model that's being fed a series of scenarios for the future. And it's giving you target outputs or target variables like temperature, precipitation, humidity. Now, Earth system models are, again, very complex. They solve differential equations all over the Earth. Takes a long time. You really need a lot of compute. To speed it up and to be able to maybe study more scenarios in a more probabilistic sense, what they have done is, in fact, take an ML model and teach it to emulate some of the processes that the Earth system model used to calculate in a physics-based manner. So with these emulators, you can then rapidly predict the outputs, even if it's a new condition. And so what that gives you is a fast approximation or a surrogate model for a given process. Similarly, we've constructed a system design here where we focus on the United States and we focus on a specific watershed within the United States. We retrieve the foundational data. That's elevation, that's land use, land cover, that's soil. We then get derivative data. Again, the centuries of flood science says that slope is very important for the occurrence of floods, for example. Having asphalt somewhere also increases flooding. So we get derivative data, which we then transform into what I'm going to introduce later as dimensionless data here. And by combining that with a database of trusted flood models, we can create our emulator to very quickly and cost-effectively get flood probability maps and flood inundation maps for our customers. So what is the foundational data, and what does it look like? What's part of the challenge here that we've been able to resolve on Databricks? So as I've mentioned, some of the foundational data is elevation, land data, land use. So this tells you, okay, which areas are developed and what are the ones that are forested. Again, very important to know. Precipitation and other climatological impacts too. Evaporation, it's not just those. This is a limited set. But the reason I'm showing you is to introduce the concept of raster data. Right? Raster data is a data model for real-world phenomena. It's really a matrix of equally shaped or equally sized cells, or pixels if you'd like, in rows and columns. And each value represents each one of those cells has a value that represents something like temperature or something else. The first thing we need to do is to retrieve that data. And what that takes is to scrape that data from public APIs that are trusted, like the Oak Ridge National Lab archives. So from the Oak Ridge National Lab archives, we need to get meteorological data, precipitation, temperature, humidity, and others. We've constructed a Databricks workflow to perform that. The first step in the workflow takes in job parameters, which you can see on the top right. These include which variables you'd like to get for what year and which tiles. Then it fans out and gets each of the different variables in parallel. Then storing the data in our geospatial Delta Lakehouse. So what this workflow has done is it's made it more reliable for us to provide the information to our clients when they need it. Public APIs are not very reliable. They go down, and we've suffered from that a lot when we know a flash flood is coming, or a client has asked us to map a recent flash flood, for example, and we wanted to go and download the foundational data, and the public API was down. We had no idea when it was going to come back. So we really wanted to, have the data in our own systems. That's why we've developed this way of storing raster data, where the data sets are stored in Azure Data Lake second generation. But we also maintain a database and multiple tables in Databricks with all the metadata you need that are related to the raster data set in question. I'm showing you here a portion of one such table for the same data set, the same DayMet data set that I've explained before. Notice how you have a description, an entity type, which I'll explain also in the next few slides, but also a shape, which is really a vector representation of the extent of the raster data set as a polygon. And that'll make it easier to perform spatial operations like intersects, for example, without having to go here, get all the data, and find the ones that matter to you. So you can directly use this data set or this database table in Databricks to find the data sets that are of interest to you. And this is how it's implemented. So our ML model, the feature engineering workflow we have, they consist of several workflows stitched together. And a lot of these workflows have to access really the same data sets. So we had two goals in mind. One, having single source of truth for table schemas, but also standardized CRUD methods for these tables, an ability to retrieve and update these tables. So we have this approach of creating a parent class, which is the database client, which exposes these get, post, put, and delete methods. And then for each specific type of data set, like elevation data, for example, you have a class that inherits from that parent class and introduces custom fields related to that. Again, for example, it might be the maximum elevation and the minimum elevation. It could be the source of the data or how it was collected. And so by implementing this approach, it makes it very easy to maintain and manage a database on Databricks with multiple tables for the different data sets that we need to access. All right, let me jump in a little bit to the data transformations here. I've discussed it briefly before. There's a lot of foundational data sets that we use, but those are typically not enough to give you a correct idea of which areas are more prone to flooding or not. Again, we know from the centuries of science that there are better things we can calculate, like the distance of a location to the stream, right? The closer you are to the stream, the higher your likelihood of riverine flooding, and the elevation from it. You can also calculate slope. Again, if you're on a slope, water is more likely not to accumulate there. We can also get a measure of accumulation. And so by combining slope, we can actually provide data and calculate data on where water is most likely to converge. So this is the derivative data we have to calculate in Databricks, right? And this is intermediate data, so we're not there yet. Really, the final thing we've looked at and we found to be the most helpful is reducing the dimensionality of our problem by getting dimensionless features. What these are combinations of the previous derived data sets to give you, let's say, if you're looking at an image, channels that have values that do not have units, right? So if you look at flow over flow capacity, the numerator and denominator have the same unit, and so their combination has no unit at all. This reduces the dimensionality of the problem while maintaining the ability of the model to capture the physics of what's happening. It also makes it much easier and faster for the model to learn the flooding process. And what we found also is that it makes the model better at capturing flooding in more diverse areas that maybe it hasn't seen before, and that have not actually been previously mapped by the government or other agencies or engineering companies. And so that's a big use case. Okay, so you've seen the large number of transformations, and these all have to be stitched in a Databricks workflow. And so what the workflow is doing is tying all the different types of data into a workflow, right? So we're making these transformations reliable. We're making them available through an API that we're able to kick off when, let's say, we foresee a weather event, let's say excess rainfall, or we foresee, for example, a river gauge going very high. Here I'm highlighting part of the software stack, mainly to highlight the pain point we've had. Specifically, GDAL and GrassGIS. Those are open source. We can use them, install them on our Linux computers. But they have been pain points because we're still trying to figure out the best way to leverage all of the capabilities of Databricks for raster processing. I've actually created a brain date for Thursday at 2 p.m., which I encourage you to join if you'd like, to discuss alternatives to this methodology for raster data processing on Databricks. Okay, final piece of the technical puzzle is every time a workflow runs, we need to log. And this improves the observability of the workflows we're trying to run. And it improves our ability to go back and see what went wrong if something went wrong, or keep track of what each user has asked for by calling our API. This follows the same pattern I've shown you before, where we have a pattern class for transaction logging and different subclasses for each of the workflows. For example, here, I'm showing you a feature engineering transaction log. And this is for the workflow I've shown you before that calculates the derivative data sets. And what you see is that it takes into account an ID for the watershed of interest, the git hash, so what code was used to generate those features, the status, is it in progress, has it succeeded, has it failed, and whether this is a debug mode and what's the timestamp. It doesn't show here, it's right behind the closed captions. And I'm showing you another one here that has slightly different, it has custom fields. And that's really the power of being able to inherit from a pattern class that has the same functionality, but you really want to adapt that functionality to your specific data sets, in this case, to your specific workflows. It looks something like this. I apologize, it's very bright in this room, but really and this is covered, but what this is supposed to show is a log it's an instance, it's an object, right? So it's a log object, and what it exposes is a way to update, the status of a transaction log, for example. It could be a queue batch or queued, it could be succeeded. And then it also exposes methodologies to get items from those log tables, let's say by status, by run ID, by location. And this is the way we've expanded our transaction logging across all of our workflows. Okay, finally, we come to the machine learning piece. Again, like a lot of these interesting use cases, the data engineering is really the most time-consuming. But now, machine learning is one of the cooler parts of this, and I'm happy to show you that right now. So the dimensionless features we've calculated, in combination with the storm conditions and the river flows, we are trained against the benchmark, which are really what are considered the gold standard engineering data sets for flood and inundation mapping. We retrieve that data right now in the United States from FEMA, and we're retrieving them in other countries too, from their own governments and engineering companies who have run these studies. So we train a neural network, in fact, a convolutional neural network, I'll explain that in the next slide, to emulate these benchmark data sets using the features we've calculated and storm conditions. So what this really unlocks is the ability for any location to input storm conditions and flows and get a flood inundation map, a map that shows you exactly where the water is going to be. We call this product Flood Predictor at Stantec, which we monitor and retrain regularly. So we use, again, a UNet architecture to enable this. UNets for flooding is not particularly a new thing. It's been used in the literature to detect and find floods from satellite images. You can actually read these two papers that I think are pretty cool that take satellite remote sensing data from Sentinel-1 and find where the floodplains are. Now, why is that good? Why are UNets good for this problem? If you look from a bird's eye view at a flooding event, and you think of the flooding event as an image, it's really a semantic segmentation problem. Which pixels in your image are flooded and which ones are not? And UNets are great at that. Mostly because of their skip connections here, which preserve a lot of the spatial information across different scales. Our challenge, like in these papers here, was to adapt UNets for multi-channel images. Again, our images are not RGB 3-channel images. They are multi-channel. In fact, they're 10 channels. And each channel represents one of the features we've calculated for the area of interest. So we had to train one from scratch. And what you get in the end is a solution where when a community comes and requests the cost-effective flood assessments, we can process their area of interest and calculate the features within 10 minutes for a resolution of 10 meters. It actually goes up to an hour or two if you're using the highest resolution available, let's say, in urban areas in the US. Some of the latest data sets are 1 meter in resolution. It's incredibly high resolution. And then once this is calculated, you don't need to recalculate it often. Now you do over the years because land use patterns change and climatology changes, but that's over a period of years. Now once you've calculated the features, you can infer using the machine learning UNet approach we've trained within a few minutes and get you, for your community, a probabilistic map of flood inundation. The reason it's probabilistic is because this is very quick. We can parallelize it over multiple scenarios, and you can get an envelope of what you might expect for your community. That's something that wasn't before possible. Some of the positive community impact. One of our first clients was the state of Tennessee, focused specifically on Western Tennessee, areas like Memphis, for example, that are highly populated. And what we've provided them is we've actually wrapped our solution with this front end that you see here, which allows them to select the area of interest using this ID code, which is actually uniform across the United States, along with storm severity, to give them a probabilistic assessment of their flood risk across their area of interest. There are now conversations about bringing that statewide for the whole state. I'm very also proud of being part of this project that just recently kicked off. This is with the Stolo community in Canada. It's actually a group of 10 First Nations peoples along the Fraser River in British Columbia in Canada. The project is not just flood hazards, right? So for a lot of these communities, flood is one of many, and it's the combination of hazards that they're interested in. So here we're looking actually at landslides and flooding. But flooding is a big component, right? So really here we start seeing the advantage of combining the latest technologies, as provided by Databricks, with the decades of experience Stantec has had to build local knowledge of the communities that they serve and how that increases, how improves how community, communities trust the data that we give them. And so we're able to provide them with these flood risk assessments and also landslide assessments. So finally, where are we going next? I've discussed flash flooding and riverine flooding, mostly flash, but we cannot avoid coastal. Most of our population lives in coastal areas, and so we cannot avoid talking about coastal flooding. Now we're developing this tool to extend our product, which we call, again, Flood Predictor, along with our partners, Microsoft and AltaML, to build the coastal flooding component of our Flood Predictor product on Databricks. And so by the end of the year, we'll hopefully have the ability to combine 3 different types of flood hazards for our clients: riverine, flash, and coastal. With that, I want to say thank you for listening to me and being here today. It was my honor to present. Please check out the QR code for the website for this product I presented, and feel free to reach out to me on this email or right now, right after the presentation. Thank you.